Okay, in our last lecture video, we talked about how we can identify electrons within an atom based on how much energy they have, and that in the end, we had individual subshells or sublevels that could each hold individually 2 electrons. So we had the S type of sublevel, which could hold 2 electrons. We had the P type of sublevel, of which there were 3, PX, PY, and PZ. Each of these can hold 2 electrons. So P subshells or sublevels can hold 6 electrons total. D, there are 5 types, so those can hold 10 electrons. And F, there are 7 types, so they can hold 14 electrons total. Now we're going to look at electron configuration, which allows us to see which of these different sublevels and which primary energy levels N have electrons inhabiting them. So let's take a look at some elements and how we model where their electrons probably are. So let's take our trusty old isotope of carbon, carbon-12. We know from its atomic number that it has 6 protons, which means a neutral atom of carbon also has 6 electrons. So we want to talk about where those 6 electrons are. So the first rule is that we fill up the lowest energy levels first. So we fill lower energy levels first. So that means we fill energy level 1, and then we fill 2, and then we fill 3, etc. And the second rule is we fill the sublevels in order. So that means we fill S sublevels before we fill P, before we fill D, and before we fill F. And we also remember, just to hark back to the last lecture, that different sublevels exist in different energy levels. So remember, in energy level 1, the only sublevel available we have is S. In energy level 2, we have an S and a P. In 3, we have an S, a P, and a D. And in 4, we have an S, a P, a D, and an F. The third rule then that we have to keep in mind is only 2 electrons per sublevel. And the fourth rule is that when you have multiple types of a sublevel, like you have 3 different P levels, electrons would rather be alone rather than in a pair first. And I'll show you some examples of this. Okay, so I just made such a big deal about how we're going to fill these sublevels in order. But you'll notice already that I have something out of order. So we're going to fill up, each one of these lines here represents one of the sublevels. This number right here represents the energy level. So we have our energy level 1 with its S sublevel. Then we have energy level 2 with its S sublevel, and the 3 versions, 1, 2, 3, of the P sublevels. So we're going to put electrons in, starting at the lowest energy level. So we're going to fill from bottom to top. But you'll notice here that in energy level 3, ooh, I forgot my 3s. That's the first problem you should notice. Is that we have our 3s, 3p, and 3d, but I have 4s getting filled before 3d. And that's just how it is. So chemistry has a lot of exceptions to it. And experimentally, one day they found out that electrons would rather go in the 4s subshell before living in the 3d subshell. They found that out and they adjusted the model accordingly. So remember, this whole thing here is just a model that represents where the electrons are found and how we can talk about the energy. So remember, we're doing carbon-12 right now that has 6 electrons. We're going to represent each electron by an arrow, and that arrow will look like an up arrow or a down arrow. So that's so that we can distinguish 2 different electrons occupying the same sublevel. So here we go. We're going to put 6 electrons, and we're going to go 2 at a time. So 1, 2, and energy level 1 is now filled. 3, 4, and that fills our 2s energy level. Now we move on to 2p. We have 2 electrons left, and this is the part where they would rather exist in their own sublevel than to pair up. So when we do 5 and 6, 5, 6. So this is telling us we have 2 electrons in the 1s energy level. In energy level 2, overall there are 4 electrons. 2 are paired up in the s subshell, and 2 exist separately in individual p subshells. Okay? Now, we call these different, we have names for these electrons. The electrons in the outermost, the highest energy level, which in this case is energy level 2, these are called the valence electrons. And we see that there are a total of 4 valence electrons here. Everything else that's left is a core electron. In that case, we only have 2 electrons left, so those are the core electrons. And this is going to be important because it's valence electrons that are responsible for when chemical reactions happen and atoms interact with one another. Okay, so this is one way to write down where the electrons are at, but we also have a shorthand notion. So let me just erase all of these sublevels that don't have electrons in them. So now we can write out an electron configuration based on where these electrons are occupying their different sublevels. So we can see from our picture here that in energy level 1, in the s subshell, there are 2 electrons. In energy level 2, in the s subshell, there are 2 electrons. And in energy level 2, in the p subshells, there are a total of 2 electrons. So this is our final electron configuration. So we have the energy level N represented here. We have the sublevel represented by here. And then the superscript is the number of total electrons in that particular sublevel. So let's do another example. Let's do sulfur. Oops, I don't mean to write in red. So sulfur, I just happen to know, since it has an atomic number of 16, we know that it has a total of 16 protons and 16 electrons that we need to organize into these energetic sublevels. So I'm going to draw them out here. Let me get them all in. I've got to draw them in reverse order so I have enough room on my iPad. Okay, so I'm going to start again putting my electrons. I'm going to fill from the bottom up because we fill the lowest energy levels first, and we're going to fill each particular sublevel, represented again by the individual lines, one at a time. So I've got to do 16 electrons. 1, 2, 3, 4. And since I have 3 of these p-type orbitals, the electrons are going to go by themselves, one at a time. So that was 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so there's how our electrons occupy these different energetic sublevels. So again, this is a model that represents where electrons are in terms of their energy. Oops, sorry about that. My dog is barking. So we can go ahead and label our core electrons and our valence electrons. So remember, the valence electrons are the ones in the highest energy level. So in this case, that's energy level 3. So our valence electrons, there's 1, 2, 3, 4, 5, 6 electrons total in that valence, we'll call it the valence shell. And then everything else, all of those electrons in energy levels 1 and 2, those are our core electrons. So then we can also write out easier electron configuration. It's a little bit easier to look at instead of all these weird looking arrows and lines. So we can count how many electrons are in each energy level and sublevel. So in energy level 1, in the S sublevel, there's 2 electrons. Energy level 2, sublevel S, has 2 electrons. Energy level 2 in the P sublevel has a total of 6 electrons. Energy level 3 in the S sublevel has 2. And then, I'm going to start saying this how we normally say it, the 3P energy level has a total of 4 electrons. Okay, one more example. So let's do nickel. So nickel has a chemical symbol, Ni. It has an atomic number, 28, and a mass number of 57. So that gives us a total of 28 electrons that we need to put on our picture. This is a lot of electrons to place on our model, so let me sketch that out. And you'll notice that we're going to fill from bottom to top, and we have this interesting little exception here, right, where 4s is going to get its electrons before 3d, even though 3d is going to end up being lower in energy because it's a lower energy level. N is equal to 3, not 4. But that's okay. We're just going to learn that this is how you do it. And that's based on experimental evidence. So the model just had to be revised to fit with experimental evidence. So let's start putting our 28 electrons in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, and 28. Okay, so now we've assigned all of our 28 electrons to the subshell that they're inhabiting. And now we're going to write out what the electron configuration is. And when we write it out, we're going to remember, though, that we're always going to write it from the lowest energy level to the highest. So even though we know that we had to fill the 4s before we filled the 3d with electrons, when we write out the electron configuration, we're going to write it from lowest energy level to highest. So that's 1s2, 2s2, 2p6, 3s2, 3p6, 3d8, and 4s2. And when we look at this, we want to look at our valence electrons. The highest energy level that we have here is energy level 4. So that means that there are 2 valence electrons, and everything else is core electrons. And again, that's important because it's the valence electrons that are going to participate in a lot of the bonding, although things get a little bit wonky when we start dealing with atoms that have d orbitals. But we're not going to talk too much about that in this class. So just to distinguish more between the core electrons and the valence electrons, so the core electrons, they spend most of their time close to the nucleus. So even when they're at higher energy levels, they're still spending time close to the nucleus. The valence electrons, on the other hand, they are at the highest energy level, so highest E sub n, and that means that they are the farthest from the nucleus. So it kind of makes sense that since they're so far from the nucleus, they are the most available to interact with other atoms, undergo chemical reactions. They are also the ones that gets lost or given between atoms to form ions, and they can be shared between atoms when we make chemical bonds. And we'll talk about that coming up.